Hi everyone, welcome back. In the last video, we looked at the impulse sensitivity function for nonlinear oscillators. And in this video, we'll continue on that topic and we'll discuss the phase noise model based on this ISF model that we derived last time. So call this oscillator phase noise. And we are using the ISF model for phase noise. Okay, so I'll leave some references in the description that you can look at. So let's do a quick review. So we said that, okay, if I have, what is the ISF? So if I have some input impulse that goes through a function, a transfer function, or you can call it an impulse response, HV of t comma tau. And then that gives us at the output some phase shift, right? So we call that phi of t, right? And then this phase shift can be put in to another function, which was based on, I guess, the kind of oscillator you have, f of omega naught t plus phi of t, right? So this one goes in there, and that finally gives you the output voltage V out of t, right? So this is a linear time varying model, and this is a nonlinear model, right? And based on this f, usually this f is, say, a cosine theta or cosine omega naught t plus phi. But, for more complicated limit cycles, that would not be cosine. It could have some harmonic content as well, right? So, I encourage you to look at the previous videos on both limit cycles and ISF models derivation before you continue with this. But essentially, we said, okay, this transfer function takes the form of gamma of omega naught tau divided by Q max times U of t minus tau, right? Where this gamma function is called the ISF, the impulse sensitivity function, right? And this Q max is the equivalent capacitance at the node at which this ISF is calculated times V max, which is the maximum swing at that node. So let's say you have some kind of oscillation at the node that you're looking at. So the voltage is swinging like this, right? So essentially this is V max, right? Of course, you need that normalization there because you want to make sure this ISF is independent of the input signal. So for example, if Vmax is very large, then for the same input injection current, the amount of phase shift would be very small, right? Because the change in this voltage would be very small. Whereas if Vmax is small, then the injection current can produce a huge amount of phase shift. So here we kind of normalize with that. Also depends on the capacitance of that node, of course, because the amount of charge generated is a function of that. And here, I guess we're assuming that the input current pulse has a fixed amount of charge. So say 1 coulomb or 1 millicoulomb, whatever it is, right? So maybe you can normalize it to 1 coulomb. So that's not explicitly written out, but every time you calculate this ISF, you need to normalize with respect to Q max. And when we actually simulate it, which we'll do in a future video using cadence, then you also need to normalize with the area under the pulse that you use. So if this is the pulse, right? I of t, use a small pulse, then you need to normalize with respect to this as well. Anyway, we'll do that when we get to the simulation part of it, but I just wanted to keep in mind what this Q max actually is. Okay, and we also saw that this model makes two assumptions. Let's quickly review them before we move on to the phase noise part. So the first assumption is that HV of t comma tau is valid, or in some sense is linear, right? So basically the I of t to phi of t is linear. And this is a valid assumption in my opinion, because the current sources from a noise source is usually small. And they actually show that in the paper that for at least certain topologies, even with very large current sources, much larger than the noise, you still have a linear response in the phase, right? So when we go to simulation, we'll see that we need to make sure that this impulse is within the linear regime when we're calculating the ISF. Right? So what you can do is you can sweep this impulse over different sizes and then make sure it's still linear, and then calculate the ISF. We'll get to that. So that's a valid assumption, more or less valid. And then the second big assumption is that phi of t is sort of independent of a of t. And another way to say that is that phi of t takes the form of a step function. Right? Again, this assumption is not fully, in my opinion, at least, it's not rigorously justified. Because in reality, actually, if you want to be really mathematically rigorous, this is not true. But for practical cases, they show that, okay, it's good enough, right? They don't actually show that experimentally, but at least in simulation, you can see that it works. So at least in terms of practical design perspective, it's a good enough assumption, let me say. Okay. So based on these assumptions, they derive this model here, this model here for the ISF. And today we'll essentially use this model to find how phase noise is generated. So the mechanisms behind the generation of the 1 over f cube phase noise and the 1 over f square phase noise, and so on, and where it comes from. And also we'll look at some design principles as to how to reduce the phase noise in a given oscillator. Okay, so we left off last time deriving this part. So we said, you can expand gamma function, the ISF, in terms of a Fourier series. So let me just write that out. So we said that, okay, gamma of omega naught tau can be written as C naught over 2 plus sigma n equal to 1 to infinity Cn cosine n omega naught tau plus theta n. And this theta n factor is not actually that relevant because the phase of a noise source is really not that important, right? And then we also said, okay, then given this expansion of gamma, then you can write phi of t. You plug that back into the original equation, this equation. Not that equation, actually. You have to plug it back into the integral, right, of the linear time varying system. That should give you, and this is sort of a review from the previous video. So if you don't know what this is, just watch that. We end here. I of tau d tau plus sigma n equal to 1 to infinity Cn integral of minus infinity to t I of tau cosine n omega naught tau d tau, right? Okay, so that was sort of where we left off. So today what we'll do is we'll use this model essentially to take different values of I. So we'll look at, okay, if I have a certain I, some current, start with sinusoidal current and look at how that can produce the phase noise skirt, right? Like what is the mechanism behind how that translates to this? And then from this through the nonlinear function into the voltage at the end, right? That's a phase modulation kind of process. So, okay, just to review, you have I of t that goes into a linear time varying system, produces phi of t, phase shift, and then that goes into a nonlinear system, and that produces V of t, voltage, right? So this is based on ISF, and this is phase modulation, right? Okay, so let's take the first example. I'll take the general case directly, which is that if I of t, say, is some function in, some amplitude, cosine of m omega naught plus delta omega times t, right? For m which is some integer, belongs to integers. And delta omega is much less than omega naught. So what is omega naught? Omega naught is the oscillation frequency of the oscillator. So what we're essentially doing is we are saying, okay, if I take any harmonic of this oscillator and I displace, I'm slightly displaced from that harmonic by this delta omega, right? And I inject a current at this displacement from one of the harmonics. How does that produce, what kind of phase shift that produces, right? That's what we want to study. So graphically, this looks something like I have a signal. So this is now omega, and I'm looking at, let's say, the power spectral density as a function of omega. Say I have my oscillator, which is oscillating somewhere at omega naught. Now, of course, I have, 2 omega naught, 3 omega naught. These are all the harmonics, right? Of course, you also have the DC harmonic 0 and on this side as well. Of course, it's the real signal, then you also have this one, right? And so on. Right, so now I'm saying, okay, I'll put a signal in, let's say maybe here, close to decline. So I'll say I'll inject a signal here at some separation delta omega, or it could be somewhere else. It could be here, doesn't matter. It could be here. Right, that is determined by this factor m, exactly where you are, and the separation is determined by this. And I want to see, okay, when I have an oscillator like this, I inject a signal close to one of the harmonics of the oscillator with some signal power determined by this in. It's all variables for now. What does that do to the phase of this oscillator? Right? What does that do to the phase of this guy? That's what we want to look at. Okay, so we have an equation now to do that. So let's assume you know what the ISF is. It has some coefficients, Fourier coefficients. Right? It has these C0 and Cn. These are the Fourier coefficients of my ISF. And I have an input signal now, I of t, which goes into here and here. So we'll have to plug it in and basically go through all the math and look at what comes out, right? It's not actually that complicated. So let's take a look. So I would say, okay, phi of t is given by 1 over q max times C0 over 2 integral of minus infinity to t by n cosine m omega naught plus delta omega tau d tau plus sigma n equal to 1 to infinity Cn integral minus infinity to t by n cosine of m omega naught plus delta omega times tau times cosine of n omega naught tau d tau. And so that's the kind of a long equation, but we'll see that with some approximations, this actually simplifies quite a bit. Right? Okay, so now that we have basically three terms here. We have this term. So we have this term, and then I guess the product of two terms. So just two terms really, right? Okay, so so to simplify this, I'm not going to actually compute this, but you can actually show that when m is not equal to 0, then since this delta omega is much, much smaller than omega naught, when m is not equal to 0, this oscillation is very fast, right? Because the frequency in here, let's use this. So this is very fast when m is not equal to 0, right? And in this case, when you actually take the product of these two things, when you take a product of these two functions, you end up with a sum term and a difference term. The sum term, let's ignore. And the difference term, right? The sum term you can ignore because m plus n is going to be very large. That'll be a very high frequency term. Okay, why can we ignore the high frequency terms? I haven't got to that yet, but okay, let's just assume, okay, the sum term is a very high frequency term. And the difference term when m is equal to n, right? This is very, so when m is not equal to n, this is again very fast. Right? So when m is not equal to n, you get the omega naught term in there, and then this becomes a very um, fastly varying argument, right? I don't know if fastly is a word, but anyways, a high frequency argument. So that the argument of the integral changes very fast, right? And then of course, when let's take maybe green, and it's very slow. This is very slow when m is equal to 0. And when m is equal to n, this is very slow. So essentially you have two time scales, right? You have one time scale that's very fast when m is not equal to n in this equation, and when m is equal to when m is not equal to 0, you have something that this thing is very fast, right? So essentially what happens is that when you integrate over an argument that's very fast, that integral doesn't really contribute to the overall value. So anyways, yes, when you have a very fast integral, it doesn't contribute. So the only contribution to this entire integral comes in when the argument is slowly varying. And you can make it more rigorous, but we don't have to go there. You can use two timing principles essentially, or a method of multiple scales to make this more rigorous, or you can compute it numerically, and you'll see that the only contribution comes in when you don't have this omega naught term. Okay, so essentially you can see that the only term that remains is the delta omega term, and then these two integrals become the same, and then you end up with you end up with in cn over 2 q max delta omega times sine of delta omega t. Because essentially we had like an integral of, we all write on the side. So this whole thing basically boils down to like an integral of cosine delta omega t tau. And that of course is sine of delta omega tau over delta omega, right? And that's what we ended up with here. Okay. So this is of course an approximation. So let's say P of t is this, and this is an important relationship, right? So what is this saying? This is saying graphically, this is saying that what you have, if you plot, let's say, the power spectral density of this signal now is P of omega, then you end up with two tones because it's sinusoid on both sides at a separation of delta omega. Okay. All right. So essentially now what we're doing is we have to feed this into, let's say for simplicity, we just feed it into, so now we have phi of t. We feed that into some a naught cosine omega naught t plus phi of t. And that gives us the v of t, right? Okay, so we know that this now takes the form of sine delta omega t, right? So it's essentially just phase modulation, right? And we know that when we do phase modulation, it essentially just creates. So now I'm looking at the power spectral density of the final voltage, right? So this is the original signal, omega naught. And then when phase modulation is applied, this creates tones. I mean, it depends on the modulation index and so on, but essentially this is what you get, right? So if we draw all of this into one picture, which is useful to do, we see that maybe I'll make it bigger. So we start from this, right? So we say, okay, if I have, let's say these are my harmonics, right? And I pick some tone out here. So let me use blue, some tone out here at a separation of delta omega. So this is the current, injected current, omega, right? Then this gets modulated down from the first linear time varying process down to two tones around 0 in SV of omega, right? And then finally that gets modulated down to, modulated up, I should say, maybe. So let's use maybe green for this one. So this was my omega naught, right? And then these signals form these sidebands. Right? And of course, we looked at only a single signal right now. And we see that if we look at this equation, it's modulated by Cn, right? So if you go back up here, yeah. So keep in mind that, when m is equal to n, the modulation occurs, right? So essentially you need to be, so if you go back down here, let me pick a different color, maybe this. Okay. So this part, since it's at the first harmonic, this would be modulated down by C1. The region here is brought down by C0 as the coefficient. And the region here is brought down by, maybe I should use different colors for this. Let's use orange maybe. So this is brought down by C0. This is brought down by C2, of course, on both sides. This is by C1, right? So the region around the first harmonic is brought down by the C1 coefficient. Right, because only there m is equal to n. Okay. And then all of this is, so once they're all brought down, then this process brings them up here again to this region. Right? This is very important. Actually, we'll use this a lot when we actually go to the design part. Okay. So of course, if you have white noise now, so kind of running out of colors here. Okay, so if you have white noise, right, you can use superposition. So we looked at what happens when I have a single tone. Of course, if I have white noise, then these regions are all modulated down again by the C0, C1, C2 coefficient. And that forms sort of a spectrum here, right? And then this spectrum is modulated up here as the phase noise. Right? It's not an exact copy, it's a phase modulation. So it depends on the modulation index, how that happens. But if the modulation index is usually small because these noise signals are sort of very weak compared to the main signal power, right? So because it's small, you can kind of approximate it as just bringing it down almost exactly. Okay. So hopefully that makes this whole process clear. So you have two processes. So you have the first process, which is linear time varying, and then the second process, which is nonlinear, right? And this is phase modulation essentially, and this is the ISF. Okay, so that's kind of gives us some insight. So for example, you can actually see here, we'll see more in more detail. But if instead of a white noise, if I have some kind of flicker noise here, 1 over f dependence, then that flicker noise is brought down by the C0 coefficient, right? And by reducing C0 or making it 0, you can reduce that flicker noise that's brought down. You can show that that flicker noise is modulated down into the 1 over f3 part of the phase noise. We will show that. And by reducing C0 coefficient of the ISF, you can kind of reduce the impact of flicker noise on your phase noise. Okay, so hopefully that is clear. Okay. So we saw at the end that phi of t is given by approximately by in Cn sine of delta omega t divided by 2q max delta omega. Okay. And we said, okay, the modulation index is small. Because it's small, we can find the total the sideband power with respect to carrier, right? So once this goes through phase modulation, what am I saying here? So we have these two tones in SV of omega versus omega, and then this goes through the phase modulation, right? So here we have omega naught, and then this becomes two sidebands, right? So essentially using basic phase modulation calculations, you can show that this single sideband or the sideband power with respect to carrier can be shown to be SBC delta omega is approximately equal to 10 log IN Cn over 4 Q max delta omega square. This is an important relationship, right? Okay, so this actually shows you where you get the 1 over f squared term. Comes from thermal noise, right? Because here we have this 1 over f squared coming in from here. And here we assumed, of course, that the noise power is uniform over the entire spectrum for I of t. And that's why we got this 1 over delta omega square, right? So that's why thermal noise in the circuit gets modulated up to 1 over f squared term. Okay. And we'll see actually that 1 over f term, the flicker noise becomes 1 over f cube. That should be somewhat straightforward, but we'll actually derive that. Okay. Okay, so this is not completely the rigorous definition or derivation for the noise part, since we've only looked at right now CW signals, right? So let's actually look at phase noise power. So now we move from continuous wave to noise, right? So let's say given a source, noise source, so I'll just assume it's the current source model, IN, right? The power spectral density is IN square bar divided by delta F, right? So we'll cover noise maybe in a different video, but this is the power spectral density. The RMS value, it's not the RMS value, this is the variance, right? Variance divided by delta F. So for delta F equal to 1 Hertz, since IN square, IN is the peak value, IN square over 2 is equal to IN square bar, right? So we can substitute IN square with 2 times small IN square bar in the above equations. So into this equation basically. Right, so we end up with the power spectral density or the noise spectral density, which was defined as the phase noise, is equal to 10 log IN square bar over delta F, the power spectral density of the noise source itself, times sigma Cn square over 8 Q max square delta omega square. Right, so this is of course n equal to 1 to whatever, infinity, or 0 to infinity, I should say. Okay, so where did the summation come from? I mean, the summation comes from the fact that all of those terms were getting modulated down, right? If you remember. Let's go back this part. So we see all of these guys coming down, right? With different coefficients. So that's why I have to have the summation in there. Okay. And I mean, we're kind of assuming that they all have the same IN square, and that's why I was able to bring the IN square out. So we're assuming thermal noise. When we do flicker noise, actually, we cannot do that. So, sorry, yeah. So since it's thermal noise, we're able to bring the IN square out of the summation, since it's the same for all of them. And then you can use Parseval's relation. So that's a theorem which has to do with Fourier transforms, Fourier series, which says that basically if you have the Fourier series of any function, then the power contained in the coefficients, it essentially says the power in time domain is the same as the power in frequency domain. But the relationship turns out like this when you have Fourier coefficients. Sorry, this is in one period. Modulus of gamma of x dx, which is of course 2 times the RMS value of gamma squared, right? The RMS would have a square root. So when you square that, you get the integral on the left. 1 over 2 pi times the integral on the left. So that's why you have the factor of 2 as well in there. Okay, so we'll substitute this term in here. And then we finally end up with the power spectral density of thermal noise that is modulated onto the phase noise, right? Gamma RMS square over Q max square times IN square bar, the power spectral density, divided by 4 times delta omega square. Okay, so this is essentially for, you can see here that actually this is the 1 over f squared part of phase noise. Okay, very nice. Next, we can do the flicker noise part. So here we've assumed sort of that, you know, this IN square bar is the same for all of them. Now we'll kind of get rid of that assumption. Okay, so we can say that flicker noise can approximate the power spectral density of flicker noise, which I'll term as, which they term, I guess, in the paper as IN 1 over f. That can be written as IN square omega 1 over f, which is the corner frequency of flicker noise divided by delta omega, right? Because it has a 1 over f dependence, so it's 1 over delta omega dependence. And this is only true when delta omega is less than IF, right? So where this is the 1 over f corner frequency. Right? Flicker noise has this kind of profile. You have the 1 over f dependence, and then that becomes flat. If you look at the power spectral density, flicker noise, it's like that. So we're saying, okay, this is the omega 1 over f. Before that, it has this 1 over delta omega dependence, and after that, it's flat. We care about this part, basically, right now. Okay. So we will essentially get rid of that summation and replace IN square with this in the previous relationship. So that gives us 10 log C naught square, since we're only looking at the part close to the origin. So we only consider C naught. We don't consider the other modulation coefficients, times IN square delta over delta F divided by 8 delta omega. And that's coming from this delta omega, right? So we've substituted this in place of this, okay? Times omega 1 over F, which is the 1 over F corner frequency, divided by delta omega. And there should be a square here, and this should be like that. Okay. Right. So basically, this term is the only term that got added at the end, right? Go back and look at this equation. You'll see that that's the case. Okay. So here you can clearly see that now there is this 1 over delta omega cube dependency, right? So let me put that in like a box maybe. And that is what you see in phase noise as well, right? So you see that typically the phase noise spectrum looks like this. You have the 1 over F cube term, 1 over F square term, and then the flat cube and flat part. So this is omega. This is the phase noise spectrum of the voltage, right? So now we see that essentially this one is coming from flicker noise that is modulated onto the phase noise, and this is coming from thermal noise that's modulated onto the phase noise, and this is actually the thermal noise of the oscillator itself, different components in the oscillator. This is the unmodulated component. Okay. Okay, so now if you want to find at what frequency this happens, this is at what frequency, what we need to do is we need to equate this term, see where this is equal to this, right? And then find at which delta omega that occurs. So what is the value of delta omega where that happens? So it's fairly simple algebra. You just equate this argument with this argument, right? And some terms cancel out, and you're eventually left with delta omega, which is the omega 1 over F cube corner of phase noise, is the 1 over F corner of the flicker noise, times C naught square over 2 times gamma RMS square. This is also an important relationship. So it shows that the flicker noise 1 over F corner and the phase noise 1 over F cube corner are not exactly the same. In fact, if you make C naught square 0, then the 1 over F cube term should go away, right? So there should not be any 1 over F cube term. Yeah, it's kind of an interesting insight, right? So maybe we should write that down. So if C naught goes to 0, that implies that omega 1 over F cube corner also goes to 0, right? Okay. So the 1 over F cube term in phase noise, you can see that it's kind of a strong function of the, what is C naught, right? So C naught, so this is the DC component of ISF, because it's the, I guess, the zeroth coefficient of the Fourier series of the ISF. So essentially, if you have an ISF that has some non-zero DC component, so in this case, like the DC is somewhere here, right? So this would be C naught. Then the 1 over F cube term in the phase noise would be large. Whereas if you have ISF that looks like this, which is more symmetric, then C naught, which is somewhere here, is close to 0. And the 1 over F cube noise, the close-in phase noise, is reduced. Right? That's the idea. We'll actually go through some design principles later, but where we actually use these techniques or these tools, or I should say these principles, to design better phase noise oscillators. But for now, we'll continue with, I guess, the analysis, right? So one thing we've kind of ignored so far is cyclostationary noise sources. Right, so what is that? So this is when the noise properties, what do I mean by noise properties? So that is the statistics, such as mean and variance, if it's Gaussian, but can have other statistics as well, are periodic. Right, so far we've assumed that it's sort of white noise, which means that the statistics are independent of time. Whereas, or it's also called stationary noise sources. But now we're looking at cyclostationary noise sources, where essentially the noise properties are periodic in time. So within a single period, they can change. And as an example, you can look at, for example, the short noise inside a transistor, right? So when current flows, you have a lot of short noise, and current doesn't flow, you don't have much of it. So current necessarily is obviously not necessarily, actually, it's not constant over a single period. And that's why noise produced inside the transistor is not necessarily constant. You could also say the same kind of about flicker noise as well, right? But other examples of stationary noise sources are, for example, resistors inside the oscillator. So the noise produced by the resistor, which is the KTR, 4 KTR times the bandwidth, that part is not cyclostationary, that's actually stationary. So we need to look at how we can treat these kind of stationary noise sources, and it's actually pretty straightforward. So you can say IN of t from a cyclostationary noise source can be treated as, just decompose it into a stationary noise source, IN0 of t times some periodic function, omega naught t. Right, so this is cyclostationary, this is stationary, and this alpha is periodic. Okay. So this is alpha is chosen in such a way that the maximum value is 1. So this should be normalized. So the maximum value of alpha is always 1. And it just makes the math a bit easier. Okay. So given this, if you go back and look at the phi of t integral, right, which was the convolution integral, that was gamma of omega naught tau divided by q max times in of tau d tau, right? So now we can decompose this into minus infinity to t alpha of omega naught tau times gamma of omega naught tau divided by q max times in0 of tau d tau, right? And this is called the effective ISF, gamma effective. So what that is saying is that you can kind of redefine the ISF to include the periodicity in the statistics of the noise source, right? You have to be a bit careful with how you do this. And when we do the simulation examples, we'll see that this actually matters the way you do it, right? So it's not included. So basically you need to find out what the cyclostationarity is of the noise source and then modulate the impulse with that same cyclostationarity and then find the effective ISF. When we do the simulation part and how to actually compute this ISF, we'll go over it, but just keep in mind that that matters, right? So just as an example, we can look at, let's say, a Colpitt's oscillator. We know that the voltage, because there's this huge LC tank over there with high Q, let's assume it's high Q, the voltage should be filtered out and you should get a nice sinusoid, but the current looks something like this actually. It only flows when the voltage is negative. So this is the current, this is the voltage, and this is Colpitt's. Right, so if you plot, for example, for this, it's just a qualitative plot, time, and let's say I'm plotting gamma, right? So the gamma of this may look something like something like this, okay? But the alpha of this function, because it's cyclostationary, only when the current flows, you really get much of an alpha. It might look like this, right? So the effective ISF would actually be blunted quite a bit. Might be like that, right? So this is the gamma or gamma effective. It should be gamma, not tau. And that's good. So now the effective ISF is weak, which means that any perturbation doesn't really produce much of a phase shift for most of the cycle. Right? So that's why considering alpha matters a lot. So depending on which noise source you're looking at, you have to make sure that if it's cyclostationary, you have to include this alpha term in there when you're calculating the gamma or when you're computing gamma effective. Okay, so that pretty much covers, I guess, most of the analytical part of this discussion on phase noise models. We can move on to some of the design implications. So we have some insight as to how this phase noise is being created, right? So you have flicker noise and thermal noise, and then flicker noise is modulated up by the C0 term. Thermal noise is modulated up onto the phase noise using the other terms, so C1, C2, and so on. So if you want to reduce phase noise, then one thing you can do is you can try to reduce Q max, right? If that's a possibility, that is. So you can have, let's say, larger swing or somewhat of a larger capacitance on the output node, then you can reduce Q max, increase Q max, and then that would reduce the phase noise, right? Because Q max shows up in the denominator of all the power spectral densities that we calculated, right? So for example, here shows up as Q max square for the flicker noise term. And again, for the phase noise term also, for the 1 over f squared term also, it shows up in the denominator. So that's one way to do it. That may not be always that straightforward, right? Then the next thing you would like to do is you want to reduce interference around n omega naught. Right? So at all the harmonics of your oscillator, you want to make sure there's no interference there because that gets modulated down by all these coefficients, right? So I mean, if it's away from the harmonics, it's okay because that gets blunted down when it gets modulated down by the 1 over delta omega term. But if it's close to one of the harmonics, then that gets modulated down directly by the coefficient itself, right? Because delta omega is close to 0 then. So if you can reduce interference signals close to any of the harmonics, that can help. But I think the most important one is to reduce C0 term in order to reduce the closing phase noise, the 1 over f cube part of the phase noise, right? Okay, so how do you do this? Implies we need to make the ISF symmetric. So it doesn't have any DC component, right? So this is done by topological manipulation of the circuits. So we'll actually go through examples and you'll see that, say if I have just a cross-coupled oscillator, which is widely used. Should be current source down here. And these should also have some kind of inductors here. Okay, and let's say I have an inductor and a capacitor here, my tank. Right, so you can actually show that this one doesn't have a very symmetric ISF with respect to this node here. So whenever you say ISF, you have to specify which node you're looking at and which current source you're looking at, right? So here I'm talking about this current source, right? And this output node. So what you can do kind of to improve this is you can make this a bit more symmetric in topology. You put a PMOS on top, essentially. And what that does is that it makes the rise time and the fall time of the oscillation symmetric, which leads to a symmetric ISF. So we'll look at these examples in simulation, but I'm just kind of drawing it now to give you an idea. Okay, so now with respect to this source, the ISF at this node becomes symmetric and the phase noise goes down. But still there's an issue of this source, right? So the phase noise, the ISF with respect to this source, from this source to this node, it's still not actually that symmetric. And we'll also look at ways how you can mitigate that, right, to further improve the phase noise performance. And you could even ask the question, is this necessary? Why is this necessary, right? So we'll answer all these questions when we get into like the circuit design part, right? So right now we're just doing analysis and get some intuition into design. So this is just phase noise models really. Okay. So I would like to conclude finally with the design procedure on how to reduce phase noise. We'll go through this more concretely when we actually do it in cadence. But essentially what you need to do is first identify noise sources. So what are all the noise sources, right? All the capacitances may have some loss, inductors may have some loss, then transistors have flicker noise, short noise, etc., and so on, right? So you identify all of them. And you also need to make sure you're careful about cyclostationary noise sources and correlated noise sources, right? So sometimes noise sources can be correlated. So we'll look at noise models maybe later, but yeah, you have to keep track of all of that stuff, right? And then you want to simulate gamma at output with respect to all the noise sources. Right? So gamma is defined for a given output node with respect to a given input source, right? So we'll simulate that. We'll see how to do that in cadence, like how to extract the gamma for all these sources. And then identify the dominant component. So which one is dominating the gamma? And of course, from gamma RMS and C naught, using the equations we have above for the power spectral density or the noise spectral density, like basically this one and this one. Using these equations, knowing what the gamma value is or the coefficients of gamma are, we can calculate that and we see which ones are the dominant ones. Okay, and then you need to find essentially that for each source, keeping in mind to take care of the cyclostationary properties and the correlation properties, right? And identify the worst case. So identify the quote unquote bad sources, right? And the fourth one is to modify the circuit topology to improve these sources, improve the phase noise. Right, so to improve the overall phase noise, we look at, okay, how can we modify the circuit topology to reduce, for example, the impact of these bad sources, right? We'll look at some examples. There are published works on this area. So that's pretty much it. So, I mean, just kind of maybe technical, but essentially we went through a quick review. So the ISF model, we said that, it's a linear time varying model that maps an input current excitation to an output phase, and then that is taken to the output voltage using a nonlinear function. Here we only looked at the cosine function, but if you had harmonics, then you can expand this f. You can expand this f in terms of another Fourier series, and then each of them has its own nonlinear function, right? So you can do that. But essentially we said, okay, this is the ISF. This was sort of a review. We defined what Qmax is and how to normalize with respect to Qmax. Typically the C equivalent that is drawn here is usually kind of roughly estimated based on the different capacitances of the transistors around that node. Okay, and then we look at how to do that in simulation anyway, so don't worry about that. And then we kind of reviewed what the assumptions of the ISF model are. Then we looked at, again, this was also part of the review. We said, okay, gamma function can be expanded as a Fourier series. And then we looked at what the excess phase noise is given a certain gamma function and an input current. Right? And we said, okay, this is the total model for the phase noise. We have an ISF model that takes I to phi. And then from phi to voltage is the phase modulation from the nonlinear function, right? That's cosine in this case. Okay. And then we looked at some equations. We took I of t, we put that into the phase model. And then we use some kind of hand wavy approximations, which can be made more rigorous, but for now, we'll just go with the hand wavy part. And we saw that, okay, the final phase for a given sinusoidal excitation at an offset frequency of delta omega from one of the harmonics of your oscillator produces a phase that is sinusoidal, right? So that essentially acts like a sinusoidal phase modulation, on top of your oscillator, and that produces these sidebands. And we saw, okay, we can calculate what the power of those sidebands is. And essentially from that single frequency model, we can expand that to consider, let's say, thermal noise, which has all the frequencies. So we say that, okay, all of these regions around the harmonics get modulated down by different coefficients in the ISF Fourier series. And the reason those different coefficients show up for these different terms close to different harmonics is because that's where in the calculation you can see that M and N must be equal, right? So that gives you the different coefficients. So that essentially modulates this entire thermal noise into the skirt in the phase, not exactly phase noise, into the phase, excess phase. And then that skirt, because the modulation index is low, gets modulated up to omega naught and forms this phase noise spectrum that is usually seen. Okay, so that's a lot of words, I guess, but eventually we showed that because the modulation index is low, we can find what the sideband power is for these modulated tones. And we use that sideband power to actually form a quantitative model of the phase noise. So we said that, okay, if I have phase noise, I can find the power spectral density of some given thermal noise source, put that in, and that gives me the noise spectral density using some basic tricks, the Parseval's theorem, for example, and then that gives me the noise spectral density for a thermal noise source at basically how a thermal noise source is modulated onto the phase noise, and that's the noise spectral density for that thermal noise source. Okay. We also took the flicker noise case as a special case. We said that, okay, flicker noise is only coming in from the flicker noise is 1 over f. It's close to the origin in the power spectral density. So that's modulated up only by the C naught square coefficient. And that essentially gives you the 1 over f cube term in phase noise. And we also looked at the difference between the 1 over f flicker noise corner and the 1 over f cube phase noise corner. And they are related by the C naught coefficient, which is the DC component of the ISF. And we said that, the DC component of the ISF can be made 0 by making the ISF symmetric. And when the ISF is symmetric, then the 1 over f cube corner can be reduced, or the 1 over f cube contribution to phase noise can be reduced. Finally, we looked at cyclostationary noise sources, and we said that we can kind of modify the ISF by including the periodicity of the cyclostationary noise source, and that can have a significant impact on the final phase noise, as we saw here. And finally, we kind of reviewed some design implications, increase Qmax, reduce C naught by making the symmetric circuit, by making the ISF symmetric, which can translate to symmetric circuits as well. It doesn't mean that if you have differential symmetry, for example, this way and this way, that would make the ISF symmetric. You have to be symmetric with respect to the node that you're looking at. So in this case, the symmetry is this way. Then we briefly looked at some design procedure on how we could use all of these models that were developed and this entire theory to actually designing circuits with low phase noise. Okay, so we'll look at, in another video, in a future video, we'll look at how to simulate the ISF and then use it to design low phase noise circuits. I'm also excited about that part. I've started working with Cadence, and I put out a video before this on how to actually get set up with Cadence. We'll start with some basic oscillator design And then we look at the simulating the ISF of a given oscillator and how to improve the ISF and things like that. So hopefully you're excited. Maybe it's a bit of a longer video, this one, but if you have any questions or if I've made any mistakes, please leave them in the comments. I'd be happy to hear from you. Okay, thank you. Have a nice day.